All right, so as we were saying, yesterday we talked about ionic compounds. We talked about naming ionic compounds. So quick review from yesterday, okay, that when we name an ionic compound, the first thing we do is we write the name of the metal, and then we write the name of the non-metal. And it ends in I, okay? That's what happens if it's a simple binary ionic compound. Sometimes we get compounds that may have a metal that has more than one possible charge. In that case, then we have to figure out which charge it has, and we have to add that Roman numeral to the name to indicate which of those two versions of that metal is actually in that compound. Okay, so just quick reminder on how that worked. Okay, if we're looking at, let's say number 5 here, okay, and I know we did this one yesterday, but we'll just use it as a review. Okay, Sn is tin, so I write tin. Okay, and then I look at tellurium. Tellurium's charge is always -2. Okay. That's right here, -2. And there's how many telluriums? 2. So how many negative charges do I have in total? 4. Okay, so how many positive charges do I need? 4. All right, so I need to get 4 positive charges out of 1 tin atom. So what's the charge on that tin? 4 plus. Okay, so then I write tin, 4. Okay, cool. Okay, so now that the smartboard's adjusted, tin 4, okay, telluride would be the name of that. Okay, so that's one of the special circumstances you wouldn't have taken in Science 9, okay, but it's not too difficult, we just have to figure out which charge is there. Okay, the other situation we could run into with an ionic compound would be if we had a compound containing a polyatomic ion. So for example, okay, if I gave you this. So if we have a compound that looks like that, we know that we still name it according to the same rules, right? So I would still write magnesium, and then I would just look up what OH is in my table of polyatomic ions on my periodic table. Okay, OH is hydroxide, so I simply write hydroxide, and it's named. Done. All right, when we're writing a formula for something that's got that polyatomic ion, okay, then obviously we would go in reverse, so we would say maybe something like this. Sorry. Okay, so I give you that formula and I ask you to just did it the wrong way. I was doing it the right way the first time. I have not had a full cup of coffee yet, guys. I'm going to make that as my excuse. Okay, so I give you this name, sodium nitrate. Right? So I write sodium's formula, okay, and I write sodium's charge, +1. Okay, then I look up nitrate. Nitrate's one that people mistake all the time. They put nitrogen in instead of nitrate, which on your periodic table is NO3. Okay, the charge on nitrate is -1. Does this already work out with the swap and drop? Yeah, they're both 1s, so I'm done. Okay, why did this one get brackets in a 2?
Because there's 2 of those.
Yeah, magnesium's a 2 plus, hydroxide is a 1 minus. So when I drop and swap, the 1 came here, the 2 went over here, and I have to put brackets around it to indicate it applies to both the O and the H. Okay. Ringing a bell from yesterday. Okay. Now, for the molecular compounds, we started talking about how this bond is very different from the ionic bond. Okay? In the ionic bond is very weak because electrons are taken or given away, okay? And there's not anything holding the atom or the compound together really after that, so it can break apart very easily. But in a covalent bond, the only way that each atom in the compound gets a full outer shell of electrons is to share their electrons with the others. Okay? That means that they have to stay together to have that full outer shell. So they are very tightly bonded. The bonds are very strong because of the shared nature of the electrons. Okay? So covalent molecular bonds are very, very strong. We're also going to talk about how some of these bonds are something called polar bonds, which means the electrons actually don't get shared equally. Okay? one of the atoms may have the electron more often, like water is a prime example of that. We'll talk about that in another lesson later, but okay, they're still very strong bonds because the electrons have to be shared.
Also, electrons have to orbit the nucleus, so what happens when they share an electron?
Well, once they're in a compound, the orbitals can change.
Okay.
Okay, and so electrons can kind of move around. Their orbits are not as defined as we once thought. Okay, so yeah, that shared electron, and this is the nature of the polar bond, okay, is that the electron that's being shared from oxygen spends more time near oxygen. Same with the one being shared from hydrogen. It's more attracted to oxygen, so it pulls in more. And essentially what you get is Mickey Mouse. Okay, you get this positive here, and the electrons spend more time over here, so this end of the water molecule ends up being negative. And that's why water can do things like have surface tension, why like a bead of water on the side of a glass will stick there, right? It won't fall down necessarily right away, stuff like that. It's because of these positives and negatives that another water molecule can come over and be attracted to this and form what's called a weak hydrogen bond. And that's what creates surface tension, things like that. Right. But we'll talk about that another day. Okay, so big thing to remember here is molecular bonds are very strong because the electrons are shared. Okay, as long as you remember that part, that's essentially what you need to know about the bonds in a molecular compound. Okay, now since the electrons are being shared, there's not a balancing of charges. Okay, there's not going to be a drop and swap that's going to determine our formula or our name for these compounds. As a result, a molecular compound can be any number of atoms of any kind, and we have to indicate those numbers with prefixes. Okay, so molecular compounds are going to have prefixes in their names. Okay? So naming molecular compounds, okay, we're going to have two or more nonmetals reacting to form a new substance. The compounds, the electrons are shared and they're very stable. Okay, the difference between naming ionic compounds is that we have to use prefixes. So if we have this one here, okay, this would be carbon disulfide. Okay, this one here would be dinitrogen. Actually, that's wrong. Dinitrogen monoxide. If that was in your notes wrong, make sure you change it. So we have to put the prefixes on here. Okay, the prefixes are, just in case you don't have them, 1 is mono, 2 is di, 3 is tri, 4 is tetra, okay, 5 is penta, 6 is hexa, 7 is hepta. If you took science in French at any point, you probably learned it was septa. Don't write that. Mr. Real, who teaches Chem 20 and 30, can't stand that. It's a trigger for him. Okay? You don't want to trigger Mr. Real. Okay? Trust me. Okay? So it's hepta, not septa. Okay? 8 is octa. Okay? 9 is nona. 10 is deca, and we won't have to go beyond that. Okay, those would be your prefixes. Very rarely do you ever use anything over 5. Okay, but we've got one example here where we would. Okay, in this one we got P4O10. So that's tetraphosphorus, because tetra is the prefix for 4, decaoxide. Now, something you'll notice in this example, the very first one, I did not put the prefix mono on carbon. Okay? We never use mono on the first element. Okay, so if there's only one of the first element, we don't write mono. I don't know why. Chemists just have to be difficult. They have weird rules. Okay, we only ever use mono on the second element in a molecular compound. Now, something else that we need to be aware of, if you guys can take out your periodic tables. Okay. What we see down here on this bottom row in this diagram, these are molecular compounds because they contain more than one element. Up here above them, we have what are known as molecular elements. okay, some elements bond with themselves in their natural state, okay? And so they come as pairs. Like whenever you say you're breathing in oxygen, you're breathing in O2, okay? Oxygen doesn't exist as a singular. It always pairs with itself, okay? It's a molecular element. And there are a lot of molecular elements, and they're color-coded for you on your periodic table, okay? All the ones in yellow are pairs, okay? So O2, N2, okay, that are Cl2, okay? There's a whole bunch of them that are pairs. Hydrogen is also an element that pairs with itself. And then you've got sulfur, sorry, not sulfur, you've got phosphorus and sulfur, okay? Phosphorus bonds with itself 4 times, so it comes as a molecule containing 4 phosphorus atoms. Sulfur bonds with itself 8 times, it comes as an octet, okay? So when you see sulfur as an element, it's actually 8 sulfur atoms bonded together. Right? So there are some molecular elements, and then there are molecular compounds. In both cases, it is the same kind of bond. It is a bond of shared electrons that is very strong, which is why you don't see those elements existing on their own. Okay? They always come as pairs.
What would be an example of like sulfur when it bonds 8 times with itself?
Well, that's just what it looks
That's
like.
just what it looks like.
Yeah, so the yellow stuff that smells like rotten eggs,
Yeah.
that's 8 sulfur atoms bonded together. Okay, everybody all right with that? So let's have you guys try naming a few of these. Actually, we'll do the first one together here. Okay, so for this first one here, we've got nitrogen. So same as before, the first thing I do is write the name of the first element, unchanged, and then I write the name of the second one, okay, with an "-ide" ending. But what prefix do I have to put on this? Tri. Nitrogen, triiodide. Okay, and I didn't need to put anything on nitrogen because there was only one, and we don't put mono on the first one. Okay, so try up to number 6, and then we'll go through those together. So I'll give you a couple minutes there. So for number 2 here, okay, we've got carbon. There's only one of it, so do we need a prefix? Okay, so we got carbon, and then we have how many iodines? 4, so tetraiodide. Okay, that I suppose should probably be hyphenated. Okay, prefix ending in a vowel, going to a word starting with a vowel. I don't know, just seems like there should be a hyphen there. I don't know for sure. All right, number 3. So we've got nitrogen and oxygen, so definitely a molecular compound. There's 2 nitrogens, so what prefix do I need? Di. Okay, so dinitrogen, trioxide. See, now that looks like it shouldn't have a hyphen, but it probably should. I won't mark it wrong if you do or don't. Okay, for number 4, we've got tellurium. There's only one, so we don't need a prefix on it. And there's how many astatines? 2, so diastatide. What do you notice I don't have on any of my names? Right, yeah, you gotta keep working on that because I know stuff have to break. Okay, number 5, I've got 2 phosphorus and 3 sulfurs. Okay, so that's going to be diphosphorus trisulfide. Okay, now I did just talk to you about how this one, when it's an element, comes as a 4, and this one comes as an 8. That's only when they're elements. They can be any number when they're in a compound with something else, just so we don't over-apply that rule. I see that happen sometimes. Okay. And then for number 6 here, I've got 1 oxygen, so I don't need a prefix on it. And then I'll need monosulfide. Okay, those making sense? Okay. Finish them off. 4 more. So for number 7, okay, I've got 3 silicone, so I'm going to go trisilicone, okay, tetraphosphide. Okay, for number 8, I've got 1 sulfur, so I don't need to write anything on it. So I'll have sulfur dichloride. Okay, for number 9, I've got silicone again, this time with hydrogen. Is hydrogen acting as a metal or a non-metal here? Non-metal. It's listed second, okay? That's how I can tell this is a molecular compound. All right, so we'll have silicone tetrahydride. And then lastly, I've got tetraboron tricarbide. Everybody all right with those? Okay, if we're going the other way, okay, that is we're going from name to formula, okay, it's pretty easy. We just go by the prefixes to get the numbers. So if I had, let's say, if I had nitrogen disulfide, how many nitrogens do I have? 1. Okay, how many sulfurs do I have? 2. Okay, that's probably not a real compound, but okay, that's how we do it. We don't have to drop and swap here. Like we said, we're not trading electrons. That's when we use the drop and swap. That's ionic compounds. Here they're going to be shared, so we go by the prefixes to make the formulas. All right, everybody good with that? Okay, so it's a little bit easier when you know all the compounds I've given you are molecular, or all of them are ionic. When it starts getting trickier is when you have a mix of both, okay? Because then you have to say, okay, that compound is ionic, now I need to apply the ionic rules to naming it or writing its formula, right? Adds in that extra step there, right? So these are a mixture of both. Okay? Some of them are ionic, some of them are molecular, some of them need a Roman numeral, some of them have polyatomic ions in them. Okay? This is more of a true test of what you would be expected to do. Okay? Identify it first, then apply the right rules and put the right name on it. So I'm going to give you a few minutes. I'll go over the first 4. And just actually, I'll go over number 1 with you right now, and then okay, I'll let you try the rest. All right, so number 1 has lithium and chlorine. Is it ionic or molecular? It's ionic. Lithium is a metal. So I'm going to apply my ionic naming rules. I write the metal's name first, I write the non-metal's name second, and end in I. Not too tough, because I picked the easiest one. All right, you guys try the rest there. Okay, so number 2 is a bit trickier. Okay, is it ionic or molecular? It's ionic. Chromium is a metal. All right, so I'm going to start out with my regular naming rules. Okay, chromium, fluoride. But what am I supposed to check about metals when I write these?
They can have 2 charges.
Right, if they have more than one possible charge, and chromium does. We have 2 or 3, right? Okay. So what I have to do is figure out, is it the 2 or the 3, so I put in the right Roman numeral. Right? To do that, remember, I look at the non-metal. Fluorine only has a charge of -1. That's it. Okay? How many fluorines are there? 3. So there's 3 negative charges that need to be balanced off by chromium, and there's only 1 chromium to do it, so the chromium must be +3. So I write chromium, Roman numeral 3, fluorine. Okay? If you didn't put the Roman numeral in that name, you would get it wrong on a quiz. All right, number 3, I've got phosphorus and bromine together. Ionic or molecular? Molecular, they're both non-metals. Okay, phosphorus is only 1, so I don't need to put anything in front of it. So we'll have phosphorus tribromide. Okay, and then number 4, I have zinc and iodine. Ionic or molecular? It's ionic, zinc's a metal. Okay, does zinc have more than one possible charge? No. Okay, it can only be a 2. Right, so we'll just have zinc iodide. Okay, everyone kind of following the process? Okay, keep going. For number 5 here, I've got silicone with oxygen. Okay, so molecular or ionic? Molecular. Okay, so I don't need a prefix on silicone. There's only 1 of it. Okay, and this will be dioxide. Right. Number 6, carbon and sulfur, ionic or molecular? Molecular. So carbon tetrasulfide. Okay, number 7, ionic or molecular? It's ionic. Yeah, technetium is a metal. In fact, it is a synthesized metal. is not an element that is found in nature. It was synthesized artificially. So we have technetium iodide. Okay, and number 8, okay, we have ionic or molecular. Ionic, okay, we can always tell it's ionic if it's got a polyatomic ion in it, okay, but also it has a metal. All right, so this will be sodium hydroxide. Okay, anybody done all of them? Okay, so I'll give you a couple more minutes here and then we'll go through the rest. They're always in ionic. Okay, let's have a look at the rest of the. Oh, I didn't turn the recording on. It's been recording the whole time. Okay, that's all right. So, for number 9 here, we've got calcium and we've got sulfate, a polyatomic ion. So this is an ionic compound. All right, so this will be then calcium sulfate. Okay, calcium only has one possible charge, so I'm not going to need a Roman numeral in that one either. Number 10, okay, I've got potassium, which is a metal, and permanganate, MnO4, okay, as my essentially non-metal, but it's a polyatomic ion, so this is an ionic compound.
Yes.
Okay, so this stuff is potassium permanganate. Anyone ever seen this stuff before? Purple crystals. Little purple crystals. They're actually quite pretty. Okay? But don't touch them because they turn your skin color. Okay? Like if you have really light colored skin, they'll turn your skin like very brown. Okay? Not that that's a bad thing. I mean, if you already have dark skin, you're not even going to notice it. But I once had a kid in my science class who never listened to a word I said, ever. And I specifically said 3 times, don't touch the stuff because it'll change the color of your skin. And a little while later I see him doing this with the crystals. And he was like pasty, okay, like really pale. I was doing this stuff's so cool, Mr. Coderre. Yeah, so are your fingers. All the tips of his fingers, dark brown. That doesn't come off. You can't wash it off. It like has to wear. You have to exfoliate off. So it was like for weeks.
So you could like
Tips.
the
The tips of all of his fingers were like dark brown. Okay. So, I don't know, I always tell that story just because it's funny and that's okay, number 11. I've got nitrogen and I've got oxygen, ionic or molecular? Molecular, okay. So, we don't have to put a prefix on nitrogen, I almost did, okay? Nitrogen monoxide. Okay, number 12, I've got beryllium with cyanide. Ionic or molecular? Ionic, okay. And so I just follow my usual naming rules. Okay, beryllium, cyanide. Okay, for number 13, I got barium with cyanide, so similar idea. Okay, barium, cyanide, it's an ionic compound. All right, 14, I have NaHCO3. Ionic or molecular? Ionic, sodium's a metal. What's HCO3? Hydrogen carbonate, it's also sometimes called bicarbonate. This is sodium hydrogen or sodium bicarbonate, otherwise known as baking soda. Okay, that's what baking soda is sodium hydrogen carbonate. Okay, and lastly, number 15, I've got PO4. Sometimes people make a mistake on this one. If it's listed like this, it's a compound. But if you look in your table of polyatomic ions, PO4 is also in there. Phosphate. Okay? Ions, polyatomic ions, cannot exist on their own outside of a compound. This is one of those weird situations where this one is a real compound, but sometimes it loses a couple of electrons and becomes a charged particle. Then it's phosphate. Okay? But we would name this according to our regular naming rules. Okay, phosphorus tetraoxide. Okay, we're doing okay with the naming. All right. We haven't talked a whole lot about if I give you the name and you have to write the formula, okay, which is also an important skill, especially when it comes to writing chemical reactions. Okay, because oftentimes I'll give you the chemical reaction in words, and you'll have to write out the equation, which is all the formulas written up together. So we'll have a look quickly at how that will work. So if we're converting chemical names into formulas, okay, first thing we do is decide whether it's ionic or molecular. Because if it's ionic, we're going to use the drop and swap. If it's molecular, we just use the prefixes to tell us how many of everything there are. Okay, so writing the formulas for molecular compounds is really easy. You don't have to even think, you just have to know what the prefixes are. Okay, but for ionic compounds, the first thing we do is we write the formula for the metal along with its charge. Then we write the nonmetal and its charge, and then we drop and swap, or swap and drop, whichever way. It works out the same either way you do it. Okay. So if I gave you this compound here, calcium nitride. So if I follow the instructions that I've got here, the first thing I'm supposed to do is write the metal and its charge. So calcium is a 2+. And the nonmetal and its charge. Nitrogen is a -3. Right? Then I drop and swap. Right? So I drop the 3, swap it over. Drop the 2, swap it over. There's my compound, Ca3N2. Okay. Pretty straightforward. There's a couple of exceptions. Okay. If I run into something like this, Manganese 4 oxide. Okay. What is the 4 telling me? It's telling me the charge on manganese. Very common mistake people make. They just write Mn4. Okay. They just write that there's 4 manganese. That's not what it means. Okay. It's telling me that manganese is a 4 plus. Okay. What's oxygen? It's a -2. Okay. Here's the exception. When I drop and swap, I get this, 2 and 4. Do I leave it like that?
No.
No, I always reduce, just like a fraction, okay? So compounds are just like fractions. We always reduce to the lowest form. So this would be MnO2. Okay, so that's one of the exceptions. If you get numbers that you can reduce, you should reduce them. It will be marked wrong if the numbers are not reduced. All right, the other exception we talked about yesterday when we had the polyatomic ions. So if I have this compound here, calcium nitrate, okay, I still follow the same rules. Calcium is a 2 plus, and then I write nitrate, which is a polyatomic ion, NO3, and it has a -1 charge. Okay, so I drop and swap. I bring the 1 here. We don't write 1s. I bring the 2 over here, but what do I need to do? I need to enclose this in brackets, so the 2 applies to the entire ion, and it doesn't look like this. That's not the same thing. That's 1 nitrogen and 32 oxygens. Okay, it is not the same thing. Okay, so we want to make sure that we're putting that 2 outside of a set of brackets. Okay, if you don't need to have a number, then you don't need brackets. Okay, it would just be, if this was sodium nitrate, then it would just be NaNO3. There's no need for brackets. Okay, in that case, because this is a 1 and that's a 1 and we're done. Okay, everybody all right with those couple of exceptions? Okay. It starts to get a little hairier when you start getting like a polyatomic ion, like nitrate, in with something that requires a Roman numeral. Like you start getting those things kind of put in together. Right? So those are things we need to watch for. Okay. Or weird ones like this one. Where's ammonium? Yeah, it's a polyatomic ion. It's the only one in your chart that's positive. Okay, if you look in your chart, all the other polyatomic ions act like nonmetals and are negative. Ammonium is +1, and it's with chloride in this case, which is -1. So I drop and swap. It's good. Okay. Little things to watch for. All right, I'm going to give you a 5-minute break. Okay, you can check your snaps on your phone, or go get a drink of water, or just go to the bathroom, something like that. But I'll give you a 5-minute break, and then we're going to do some more practice of this naming stuff and kind of see how we're doing. Okay, so we've covered just about everything except for one thing. Shane just brought that up to me, and that would be, what if I have a multivalent metal and a polyatomic ion, and I'm trying to figure out the name? Okay, so the example that I just showed her is if I had this. Okay, so if I have lead, which is a multivalent metal, and it's bonded to nitrate, okay, which is a polyatomic ion, how do I figure out what Roman numeral should go on lead? The answer is exactly the same way you would if this was lead with chlorine. Okay, it works exactly the same as in that situation. So what I would do is I would write out the 2 names first, lead and nitrate, and then I would look at what's the charge on nitrate. Okay? The charge on nitrate, according to your table of polyatomic ions, is -1. How many nitrates are there? 2. So there's 2 negative charges, which means this one lead has to have a charge of +2. Right? So you treat it like you would any other non-metal, okay? And you figure out the charges from there. Okay? It doesn't really change what you do. right? But it wasn't an example I had gone over, okay? So just so we've seen one like that, okay? Now we know how those ones work as well. Okay, so like we said, for molecular ones, we don't really need any rules for writing the molecular formulas. We just read the prefixes and write the appropriate numbers beside, okay? Should you reduce the numbers on a molecular compound? If I was to get, let's say, this, not that I would, but let's say I had dinitrogen tetraoxide. Should I reduce that? No. The prefixes told me that's what it is. Okay? I only reduce in an ionic compound because it's a charge balancing thing and it would actually be like the lesser number as a molecule. But if we're talking about a polyatomic ion, if they told, or sorry, molecular compound, sorry, they told me there's 2 nitrogens and there's 4 oxygens, don't change it. Okay? So we only reduce the ionic ones as a result of a drop and swap. Okay? If the prefixes tell us this is how many there are, that's how many there are. I can't think of a situation where that comes up, but maybe it could. All right, so what I want you guys to try here is I just put into Google Classroom the keys for several of the worksheets that are in your workbook. All right, so if you go to your workbook in Classroom, okay, so it's in classwork, right, and it's in the chemistry notes and workbook package. Okay, so you can see that I've put a few new files in there. Okay, these are all the keys for all the worksheets that are in your workbook. So the first thing you want to have open is the workbook, okay, which is this one here, the worksheet package. Okay, we've already done the atomic theory questions, so we can skip past those. All right, so the first worksheet is writing the formulas for these names. All right, so you can start on those, and you can check them as you go because the keys are in here. All right, you just have to find the right key. And I think it's this one. Nope, it's not that one. It's not that one either. It's not that one. It'll be the last one I try because that's how I. No, not that one. That's the one. It scanned very badly. I think actually I took a picture of this one. But okay, so that's the key. I know it's my handwriting, so it's crap, but I think we'll still be able to check it. Right, but all those are in Google Classroom, so you can check them as you go. I'll leave the actual worksheet up on the board here so that I can walk through any ones that give you trouble. Okay, but like I say, you can check back and forth. Now here's the thing, guys. When you're doing these worksheets, check your answers frequently. Okay, like do 5 at the most, and then go to the key and check that you've done those 5 correctly. What I find a lot of people do is they'll do like the whole sheet, and then they'll check them, and they'll find out they've done like a bunch of them wrong, and then all they've done is practice that bad habit 50 times. Okay, so find out if you're doing something wrong right away. Do 5, check the key. Do another 5, check the key. All right, so I'll walk around here while you guys are working on that. If you have questions, I can help you out. And let's just say do a few off of this one, then do a few off of one where you're naming instead of writing the formula, just so you get some practice of each. Tomorrow's quiz, which I will post at the end of the day today, so it should be up by 3:30, will have some stuff on atomic theory and some stuff on naming. Okay, so there'll be a little bit of each, but you'll get that tonight. Okay, so you can try it at home tonight and be ready to write it tomorrow. Right, so I think we'll probably be working on just this practice stuff for the rest of the period. Okay, but like I said, I'll be walking around. If you've got questions, just ask. Okay, you don't necessarily have to do this whole sheet all at once. Do 10, 15, and then try a worksheet where you're doing the opposite, where they're giving you the formula and you're writing the name, so you can practice both ways. If there's any ones that really give us trouble, we'll do them together.